Good morning, good evening, and good afternoon from wherever you might have joined our very first International LIDT webinar. A very warm welcome to you all here live from Hilase Center, Czech Republic. My name is Boan and I will be your host for today's webinar, which solely focuses on laser induced damage threshold, in other words, LIDT. Our presenter today, Dr. Jan Vanda, who is the head of our state-of-the-art LIDT laboratory, will take you on a journey through the magnificent world of laser-matter interaction and will help you understand the importance of LIDT measurements for laser applications and how LIDT testing can help your business. However, before we start, I would like to inform you on a few organization points. Our 90-minute webinar will start with a presentation of Dr. Vanda and will follow a Q&A, and a Q&A session will follow. Therefore, we kindly ask you to save all your questions for the Q&A session or use the chat box to place your questions, and we will get to these during the Q&A session. Though we strongly encourage you to join us in the final Q&A session for a live discussion, thus we also kindly ask you to use the hand raise button to place your questions. I hope I've covered all the formal information you need to know before the webinar. So now, ladies and gentlemen, I would like to welcome Dr. Jan Vanda, who is our expert in the field of LIDT, to take you on that promised journey to explore the essence of LIDT at Hilase. Jan, the floor is yours.
Thank you, Boan. So, as my colleague Boan said, good morning, and I welcome you also on our Laser Induced Damage Threshold webinar, and we can start right now. Just find the right share. And okay, let's do the slideshow. So, a laser induced damage threshold, and our topic today and our agenda will deal with the laser damage mechanism and main precursors leading to the laser damage, then the methods of the LIDT testing and typical cases of the LIDT test users. I will briefly describe our LIDT testing capabilities and importance for laser applications, and finally I will present you our latest results when we use the LIDT tool, LIDT test, not just as a test but also as a tool for certain process improvement. So first, about the laser damage mechanism. Laser damage is basically quite simple event. You just see the hole on the surface of whatever you are exposing to the laser beam. However, there is a quite complex background where you have to consider both material properties, which can be transparent or opaque, crystalline, amorphous, absorptive or not absorptive, homogeneous, birefringence. You can have metals and dielectrics and semiconductors and all kinds of different properties of the material which are acting and which are having a role in the damage mechanism. And then you have also the laser, which has also its own properties as wavelength or pulse length, single and multi-mode regime, the exposure duration, the pulse duration will play quite a significant role. Also the spatial profile, spatial intensity profile of the beam, polarization state, stability of the laser. All these factors will affect whether you will damage your component or whether you affect your surface you will treat effectively. Now, let's talk about the effects we are observing during the laser damage. Let's consider them in the scale of intensity, which is acting on the material. So as the intensity of the laser impacting on the material increasing, what we see first is absorption and effect which is related with the absorption with heating, and if the heat is high enough, then the melting of the material. So that's the very first thing you will see if you're using CV lasers or long pulse laser. Connected could be shock waves propagation, because when you are heating a lot, you are inducing the stress into the material, which is then demonstrated as a shock wave spreading through the bulk, which is related with the morphology changes, which is the effect you can observe when you are increasing the intensity further. As I said, there are shock waves. These shock waves can be quite dramatic, as if you have intensity enough, you will create a plasma on the surface, which is expanding rapidly. And from the material point of view, this is basically explosion, and the shock wave of this explosion is propagating inside the material. The electric breakdown is something what you can observe, particularly when you are using the electrics. You are basically increasing the intensity at the point which is exposed to the laser beam until the intensity of the electric field is strong enough to overcome the band gap of the material itself. And then we can talk about so-called phonon scattering. That's basically direction of the lattice of the material when absorbing the energy and releasing in the form of the vibration of the lattice. And finally, electron scattering, where basically electrons accelerated by the high intensity of electromagnetic field from the light acting on the material are getting scattered and releasing their energy to the material. And as we increasing energy or intensity even further, we are getting more to the fundamentals, fundamental interaction issues, and it's getting more and more complex. At high intensity, we can again dealing with the electron scattering, but not just this. We can observe multiphoton absorption and multiphoton ionization, and basically effect when there is so many photons that they can be absorbed two or more photons at one moment, even if they don't have enough energy to overcome the band gap of the material. If they are absorbed simultaneously, they can eventually overcome this band gap, which leads to the fact that the absorption is not anymore proportional to the intensity acting in the material, and we are starting to dealing with the nonlinear effects within the material. And if we increasing the intensity further, either by shortening the pulse or just by adding more power to our laser, we can see others like avalanche ionization or even tunnel ionization. So we can also observe what is happening in the material in the time scale. And this is different for metal semiconductors and the electric, because what is primarily interacting with the photons are electrons, and what we can see in the metals is at the very beginning photon electron heating, while in the semiconductors and the electric spheres you need to generate some free electrons by accelerating them with the or by affecting them with photons, by photons. And then there is many others effects happening as the time elapses from the initial exposure. I will not go through all of these, because here it is getting quite complicated physics behind that. What we just may consider is that what is in general happening in time scale is that first we have non-linear effects as multiphoton ionization, self-focusing, basically all things which are happening when the light is getting scattered by electrons. This is happening in the sub-picosecond regime. When we continue with the exposure, we can see electronic atomic subsystem relaxation when the electrons are releasing the energy they are gained from the photons, and they are recombinating. This energy released into the material leads to the generation of thermoelastic waves, which are propagating through the material. The propagation of thermoelectric waves leads to the plastic deformations and eventually to the first damages, which is usually demonstrated by cracks or voids in the bulk. And this is happening basically in tens of picoseconds to hundreds of nanosecond time scale. And when we are getting over the 100 nanoseconds, we have to also consider the thermal conductivity effect, because now the heat is starting to act in the material as well. So that's what's happening when you are using different lengths of the pulses and you are exposing the material or your element to the different laser pulses. Now, not just the sole pulse length is acting here, but also how many pulses or how long is the material exposed to the certain intensity or to the certain fluence. What we can see on this video is basically when the exposure starts, you can see that here is kind of darkish area. This is the area where the light is interacting with the material, and free electrons are getting generated, which is increasing the absorption. At a certain moment, the system of electron recombination and excitation over and over again, releasing the energy into lattice, eventually leads to the creation of the damage precursor, to the small absorption centers, which are getting growing and growing when the more pulses are incoming to the interaction. And then you are ending with the catastrophic damage, with the crater formation, because the absorption is still higher and higher and the light is getting absorbed more and more and more. So finally, after 100 pulses, you are ending with such big crater. What should be also considered when we are talking about laser damage is synergy between the material and the laser properties, because they are not acting solely, they are acting simultaneously, which could be very nicely demonstrated on absorption and reflectance, because they are driven both by the wavelength acting on the material and the material properties themselves. When you consider absorption of the metals, you can clearly see that there are some absorption peaks where all the light will be absorbed very well, depending on the wavelength, and also the regions where the absorption is very low, and that material will basically reflect everything which is impacting the material. So wavelength matters. It matters also from the point of view of the reflectance, because for the short wavelength light, for the UV or blue, some surface could seem very rough. However, when you are increasing the wavelength and you are going to the longer wavelength, then the surface from the light point of view can be seen as completely flat and basically act as a mirror. This is often happening when you are using, for example, CO2 laser at wavelength 10 microns. So even the surface which you consider in the visible spectrum as quite rough act as a very good reflector for this longer wavelength, and then the interaction is not as desired, because usually you want to cut with this laser and then you are reflecting. From the other point of view, it's good if you want to use reflector for this particular wavelength, because then you don't have to care so much about the surface quality. So that's about the mechanism. Now let's talk about damage precursors. When we are talking about the laser damage, we can essentially understand the precursors from the point of view intrinsical. This is something we can't affect and come to us related with the material of the component itself or with the technology of the preparation of such component or from the physics of the laser metal interaction itself. However, when we consider extrinsic damage precursors, this is something what we can affect by our behavior, by the way how we are handling the respective element or how good laser we are using when we are exposing the element to the laser beam, or how good clean environment we're gonna prepare for our utilization of the laser. So just briefly about the intrinsic precursor, because again there is a lot of physics behind that, and we are not here to listen to the physical lectures. This is a very descriptive picture what is in general happening when the light is uh, passing through the solid material. So first, you can see, as I mentioned before, that the behavior is different for different polarization. Usually, or what is commonly understood, is that p polarization is from the damage threshold point of view worse than the S polarization because the E field enhancement on the interface of two different media with different effective indices is higher. We call it E field enhancement, and you can see that when this electromagnetic wave of certain polarization is passing through the material, there is enhancement of the E field, which is essentially the uh, the reason why you see damage in such material. Because if the E field is higher than the critical value, and the critical value which material can handle, you basically damaging the material. This can be very easily related also with all kind of inclusions or contaminations which you can have inside the material. Because again, if you will have a small piece of dust, for example, in this multi-layer, then on this small piece of dust, you will see again this E field enhancement, which is proportional to the difference of the refractive index of these two media. And because the particle, the contaminant will be absorptive as well, you will simultaneously increasing the E field intensity and heating the surrounding material. And the consequence of such effect can be just one, and that is creation of the void, more absorption, and finally destroying the structure of the material information of the crater. So that's about the intrinsic precursors. Let's talk a bit about extrinsic precursors. What we can see here is mirror dust contamination issue. On the picture left, you can see a mirror which has some dust particles on the surface. It doesn't seem that bad, but when you take a microscope image of such element, then you see that the surface is very dirty, it's quite messy, and all these darkish spots will act as absorption centers for the light which want to pass through the mirror. So the contamination, that's a big issue. Even bigger issue can be if somebody tries to clean such contamination unprofessionally. In this case, somebody took this mirror, took a piece of cloth and tried to polish it as a I don't know, as some kind of kettle. Of course, when you do it in the improper way, all these dust particles on the surface, which may be even harder than the surface of the mirror itself, are acting as a abrasive on the surface, and you will induce such scratches or even such uh, digs on the surface of the mirror, and of course this is not helping in the element performance or its damage threshold. All these surface modification will again lead to the enhancement of the electric field if the line is passing through them, because there will be like larger surface on the boundaries of these scratches. Now it's not just about the contamination, it's also about the beam itself. You should be quite careful when you are considering your beam profile, because usually what you have is just some average value of the intensity or energy or whatever, and the vague notice of the beam shape. However, when you look on the beam carefully, this is a particular example of the square top head beam, you can see that locally in the beam profile, the local intensity can be double or even more than is the average intensity of the beam itself. And of course, in this specific point, any element you put into the beam will be stressed by more than double of the intensity, and you can easily overcome the damage threshold of such component. So that's one thing from the point of the laser which should be taken care of. The another is what is also mentioned previously is the fact whether you are using multi-mode or single mode laser, using the multi-mode or single mode regime, because in multi-mode regime, although the total length of the pulse is the whole envelope, in effect, what is happening is that the modes are exhibiting something which is called mode beating, which is eventually lead to these temporal spikes of the intensity in the during the whole pulse. So basically, you have hundreds of picosecond long uh, moments when your component is exposed to again double or even higher intensity than is the overall average of the pulse. So this factor has to be taken into account as well. We can then progress to the damage demonstration, because damage precursors are usually related also with the way how the damage looks like. On the first image here on the left, you can see the typical example of the pits or pinholes. This is something what you often see when you have intrinsic damage precursor, especially when you have some dielectric multilayer and you have some contamination, either a dust particle or some inclusion due to the material impurity. Usually these defects are very absorbent, very absorptive, and when exposed to the laser beam, they're getting heated and they create a small void just beneath the surface, which usually looks or is demonstrating like this so-called pinhole. Another thing which is related with the bulk absorption are blisters. You can see the blisters when you have some absorption uh, in the bulk material itself, and as the area is getting heated, thermally it expands and eventually it led or it can lead to such a blister like defect or damage. Another What is often observed, especially when you are testing about amorphous materials, are phase changes when the material gets heated, and this heating leads to the particle crystallization or semi-crystallization at the affected area, which then, of course, has different optical properties from the interactive light point of view. What you can see on metals is usually melt and solidification of the affected zone, which usually leads to this formation of the tiny bubbles on the surface. Again, uh, this acts as a other precursor because it's increasing the absorption when you continue to expose such site to the laser light. Now, what is happening in the bulk, or what can you see in the bulk when you tighten the light in the bulk is a void formation. This is something when you dramatically exceed the damage threshold of the material, you basically ionizate the area in the material and the plasma expands very rapidly, which creates a huge cavern inside of the material. If the event is not so dramatic, it won't eventually lead to the void, but it will demonstrate it by the crack of the whole material, which is propagating through the bulk. And last but not least is something very typical what you often see when you are dealing with mirrors or anti-reflecting surfaces and you are damaging them, because surface typically has much lower damage threshold than the bulk itself, and then you can see such beautiful craters. The left side is from nanosecond pulse, right side is from picosecond pulse. The nanosecond, very typical, you see the dark ablation area and delamination on the edges and the material ejected from the crater and redeposited on the site of the crater. The picosecond looks more dramatic because there is higher intensity, the energy comes in much shorter time, so the plasma expansion is much more rapid, and electric particles from the crater area are smaller and fly further, which is this typical tail you can see, especially when you are damaging under some angle. So that's about the damage we can see or we can observe during the laser damage process. I will stick for a short while on good practice because this is something what we can do to prevent such catastrophic damage. The first is clean environment because, as I said, the dust is one of the main damage precursors what we can affect by our behavior. Of course, not everyone can have this experiment or his setup or whatever he's doing in the clean environment, clean room, but it's always important to respect the fact that the more cleaner is the environment in which you are working, the better servability of the components which you are working will be. Also, the storage of the optical elements, if you are changing them regularly, is quite important. Preferably, you shouldn't have them lying somewhere on the shelf. You should enclose them in a proper box. Best is if the surface of the element is not touching to anything. The environment should be free of humidity. The element should be handled carefully, etc. All these are good practices which will help you with maintaining your elements safe and preventing the damage. The handling important. Always use gloves. In past year, we also all see that the face mask doesn't hurt anyone, and it may prevent to contaminate the surface of the element you are using. And last but not least, proper cleaning and proper cleaning procedure is quite important when the cleaning is necessary. So that's about the damage precursors. Now let's talk about the LIDT test methods. The methods for LIDT testings are standardized. They're ISO 21254 standard series, which are describing them. And these standards is defining laser induced damage threshold as the highest quantity of laser radiation incident upon the optical component, for which the extrapolated probability of damage is 0. When we talk it in the more human way, basically the damage threshold value is a statistical value obtained from a set of experimental data, meaning that first you have to have something which you're gonna measure, then you have to statistically evaluate your data you get from your measurement, and from this data you can have or you can obtain LIDT. The standardized procedure are basically two kinds. First is used to determine the damage threshold itself. Second is to determine the energy handling assurance. This will not tell you the damage threshold, but it will certify your component to handle the specific energy, or at least to tell you the probability at which the component won't be damaged. It describes the demands for the beam quality, particularly regarding the stability and the tolerances. It describes also the ways of damage detection and how you recognize such damage, and it gives us a guide for results evaluation. Basically, the standard basically tells us what should be included into the report from the LIDT testing, so such test is reproducible, and the reproducing facility will end with the same value as we measured. So let's jump into the particular test. ISO 21254-2 is describing two types of tests, the one-on-one and S-on-one. One-on-one test is a test which is described as a procedure at which certain position, certain spot on the sample is exhibited to exactly one pulse of a specified property, energy, and the beam profile. You are observing whether the exposed position is damaged or not. And if not, you can increase the energy on further spots until the damage is observed. Out of this data, you can calculate the probability of the damage for the certain fluence. And from this certain fluence, you can extrapolate damage probability plot and find out what is the extrapolated zero probability of the damage. This is the typical example how this test look like, and what are the results of such test. Second type of test is S-on-one. It's basically the same like the previous, but you are increasing the number of the pulses which are impacting on the specific tested position. The result of this test is so-called characteristic damage curve, which is describing how the damage threshold is changing with the increasing number of pulses affecting the one particular position. For a specific number of the pulses, you can plot essentially the same plot as in the previous case. So you can have, for example, 1000/1 damage probability plot, which is telling you what is the extrapolated damage threshold for 1000 pulses. This is particularly useful if you want or need to predict the servability of the specific component, because no one is using the mirror or lens for single shot. Everybody wants it, to use it as long as possible, and this is telling you at which fluence you have the best probability that the component won't fail even after millions of pulses. Now, ISO 21254 is 21254-3 is talking about assurance. In this procedure, we are not looking for the damage threshold itself. Rather, we are defining a kind of pass-fail test where we are certifying specific element for energy handling or power handling capability. There are two types of tests. First type is based on statistical confidence level calculation, where the provider of the sample specify what probability he expects to have damage, and then the overall surface is tested at the respective fluent, and it is counted whether or is counted how many damage states are initiated, and calculated whether this probability is fulfilling the requirements. Type 2 test is simpler. The assurance area is given by customer, so there is no statistic, no confidence level provided. Basically, customer tells that he or the sample provider tells that he doesn't want to see any damage, for example, over 10% or 20% or the whole surface, doesn't matter, for fluence 20 joules per centimeter and 1000 pulses. So you simply expose given area to the given fluence and then evaluate whether you observe the damage or not, and accordingly you declare that the element passed or failed. In this particular example I have on the slide, you can see that we tested 19 positions with the total surface area, if I remember correctly, 30% of the clear aperture or 25% of the clear aperture, and we were supposed to say whether the element withstand the fluence or not. And from the results, from the micrograph of the exposed surface, you can clearly see that it won't. Almost all exposed sites were damaged, so this particular test was failed. Now, there are also methods which are not included into ISO standards, so the values are not statistically valid, and you can't use them to declare conformity, and usually you can't even use them to compare among different facilities. So if somebody do for you RAM tests, OneonOne test, and you will require somebody else to do the same, he probably won't give you the same result because the conditions for reproducibility are not fulfilled. A RAM test basically means that you are increasing the energy after a certain number of the pulses or certain exposure duration until you see the damage. It's very useful where you have when you have a limited space on your sample, when you have very tiny sample, millimeter or 2 millimeter in diameter, so you can fit more testing positions on the surface, but you want to know at least approximately what is the damage threshold. The risk or the factor which is affecting the result is the fact that you are conditioning exposed site when you are exposing the same position to the more and more pulse. Similarly, is this method which is called Raster Scan, which is similar to ISO 21254-3 method. However, there is no confidence level or assurance area. So again, it's not statistically valid because you are not fulfilling the reproducibility criteria for this kind of test. Also, similarly, like the standardized method, it doesn't provide a LIDT value. Rather, it just tell you whether the components survive or not. And because it's usually related with certain overlap of the pulses which are affecting the surface or which are shot on the surface, they are quite this method is quite suitable if you are suspecting that there are contaminations or defects on the tested element and you want to activate them. So you can use fluent, which is essentially lower than the damage threshold of the coating, for example, but it's high enough to activate the defect, and then you can see whether the defects are present or not. So that's about the method. Let's demonstrate them on typical case of LIDT test. Now, this test is as OneonOne test. It's very common when we are testing some optical element which wasn't large enough to provide enough statistical data. So the vendor provided several pieces from the same batch, polished by and coated by the same procedure. So we can actually aggregate the results. This is the example of the ISO standardized protocol, where you can see what are the test specification, particularly what laser was used, then the procedure specification. So this is information about what was the dimension of the beam, testing the component, what was the focusing system, how was the energy of the beam handled, what was the environment, temperature, humidity. Also, what is quite important is the error budget, what tells you what is the error level of the results you are providing. Then the test parameter itself, which is telling like what is the surface, what is the tested position distribution. Then the indication of the damage status after the test of specific samples, and finally the damage probability ramp fit. So this is the case when the vendor required the damage probability for 1000 pulses, and you can see that for this number of pulses we found this damage threshold, which is defined by the extrapolated value based on the statistical data we obtained. It is always accompanied, the report itself is always accompanied by the annex with micrograph of typical damage sites. Usually it's a criteria when you exceed the damage threshold significantly, but you can see also other kind of damage. This is the pinhole case, for example. So when I showed the typical test results. Let's talk about Hilase testing capabilities, what we are do here and what we can test here. Essentially, we are using, or essentially we are focusing on pulse lasers, nanosecond and picosecond. We have single longitudinal mode laser at 1030 or second harmonic 550 nanometers, producing 1 picosecond at 1 kilohertz repetition rate with energy up to 20 millijoules, which is round Gaussian, so we can focus the beam and it's scalable from 200 microns up to 3 millimeters. We also have nanosecond system at 1030 or 550 nanometers at 10 hertz, which can go up to 1 joule. Again, around Gaussian beam, 400 micrometers is fixed. For these kind of sources, we can determine damage threshold with better than 10% uncertainty. So very precise measurement, very fine results, very good and accurate damage threshold. We also dispose with the large top head beam, again nanosecond, which can go with energy up to 6 joule. It's a square top head. The beam size is 3 by 3 millimeters, so perfect for the large optics or for the assurance measurement. And aside of this, we also have continuous wave system at 940 nanometers. This is very high power, 13 kilowatt, and mid-AR 1900 nanometers, which has 200 watts. We are able to test optics up to 6 inches diameter with limited aperture 100 millimeters, or total size 100 by 100 millimeters, and up to 1.5 kilograms. We are not limited with shape or to opaque or transparent, and we can test for angle of incidence. We can even offer the testing in the vacuum or non-corrosive gas presence up to 2 bar. And indeed, we are offering ISO compliant procedure or custom procedures and providing ISO compliant report from the test. Yeah. So this is our LIDT testing laboratory. You can see here beam distribution system. These are the pipes which are taking the laser beams on the table. Assembly for the beam management and beam diagnostics, and on the right corner you can see our experimental chamber in which are the tests conducted. This is the inside of the chamber with the damage diagnostic camera and the sample hole itself. It's 2 cubic meters volume high, so we are able even to ensure high cleanliness even during the test, because the particles have enough space to travel and diffuse from the experiment site itself. It's not getting aggregated at one point. The procedure and diagnostics is automated, so basically we just set up all the conditions and then the process is going automatically. And regarding experience, we are testing anti-reflection coatings and hydroelectric coatings. That's kind of regular testing we are doing for long, and we have some experience. We also did quite amount crystals and special glasses, or in general special materials. Yeah, this particular example is a YAP crystal tested by S1 method. We have because we are capable to handle large scale optics. We have experience with large scale optics and special applications. This is the demonstration of the optical fiber test when we were using ramp procedure to test the transmission capability for nanosecond pulses. And here we can see the damage even itself. Now, what is kind of our state of the art is our test with the top head beam 3 by 3 millimeters. This is our top head, and this is the results you are getting out of it. So we can basically combine the raster scan and S-on-1 kind of test to see the performance of the optics. This is the example when we use the top hat test to test the absorptive coating. You see that that test was basically failure because the absorptive coating was burned at the fluence at which it shouldn't be burned. This is the test of the anti-reflection coating on the yak crystal with the big beam. Due to these different conditions, we can do also some comparative investigations. And what you can see, this is the example of the HR coating test at 45 degrees angle of incidence. And you can see that with the different beam parameters, different size of the beam, we were able to have different different values of the fluence. This is understandable because by the definition of the test and of the parameters you are putting in the test, you are getting results accordingly. Or any test is a tool which is devoted to different purpose. For example, if you are testing standardly S-on-1 or one-on-one with Gaussian beam, you have very low probability that you will find a defect, but you will have a good information about what is the actual damage threshold of the coating, for example, because if you are, for example, manufacturer, you would like to know whether this coating is better than the previous, or this particular coating technology is producing better results than the previous, and then you can handle the defect. Because if your sample will be defect free, the overall performance will be will be close to the results you are getting from the testing with the small. Then you can compare raster scan with the small beam and raster scan with the big beam. And again, there are different factors which are getting into your test. With big beam, you have much better. You are much more accurate. You have better chance that the activation of the eventual defect will really happen, etc. So this you can use to compare the performance at different conditions under different circumstances, and it can be used, for example, in evaluation of specific components for the specific use. Now, I will briefly speak about the importance of the damage threshold testing for laser applications, because that's mostly the niche of what we are doing, why we are doing what we are doing, and to who we would like to provide this service. So as a facility in general, we are devoted to development of high average power pulsed laser and lighted application. So naturally, the damage threshold of the components we are using in the lasers are important for us, but as well, the damage threshold is important, for example, to determine precisely the processing window when you are using this pulsed laser for micromachining. That's also also quite important and nice use of LIDT testing, because we want to be as accurate as possible. We are following ISO standards, and we do care to have very precise assessment of the beam parameters, etc. So we can provide very good accuracy, as I showed before. And in general, we are providing this service to optics producers for R&D of new components or processes, or just to maintain the production quality, and also to provide end user certification if required. Then laser developers and laser-based integrators, to who we can provide either the assurance, reliability testing, or in the form of consultation. We can provide a risk assessment based on our knowledge of the damage threshold. And last but not least, laser end users, when they are developing optimal manufacturing conditions. We can test the materials, tell where is the ablation threshold, measure the ablation efficiency, provide on-site damage diagnostics to see what is happening when they are treating specific component with laser, and help them to determine processing window assessment. So that's our message. That's what we want to do, and that's what we are doing at the moment. And now, as I promised, I will show you example of how we used our laser-induced damage threshold as a tool for improvement. So what we were doing was basically we were required to optimize process of glass drilling. Well, at the first step, we were using our PerLab system at 10 nanometers, 1.8 picosecond, and energy up to 10 millijoules. And the task was find optimal conditions for volume modification. That was important that the damage of the surface is undesirable. However, the energy or fluence has to be sufficient to induce the material modification. And then also to find a way how to efficiently remove the material for the laser micromachining without cracks or irregularities on the edges. So the problems basically, as we found out, is that the processing window of the glass treatment was very vague. The ablation threshold was somewhere between 4 and 9 joules per centimeter, and no one was actually sure what is the real value. And then also the lack of beam diagnostic. This was the problem of the process itself. So the process has very low repeatability. On the micrographs down here, we can see the results. You can see that either the beam was below the was far above the ablation threshold, so you cause this very irregular hole on the surface, or you've been causing the cracks around the affected zone, or the energy was not sufficient to do anything but the burn surface itself without doing what you really want to do. So what we did was that we took the sample of the glass which is supposed to be treated, which was D263 glass sheet with 100 microns, and we did S1 to find out what is actual damage threshold for the material, which we found it's close to 4 joules per square centimeter. We also measured what is the probability of the phase change without damaging the sample itself, while ballistic damage while damage was defined as a ballistic crater observable by 20 times magnification, while phase change was defined as a color center with no crater. And from our data, we also extrapolated what is the 100%, what is the lowest fluence for the 100% damage probability. So this is basically the ablation threshold at which you always see the crater or always ablate your material, but you won't overcome the intensity or the fluence on the surface of the material to have these undesirable effects. And when we took all this data together with the beam diagnostic provided by the LIDT, because you can see that the margins between the 0 and the 100% damage probability is quite small. It's like 10% of the damage threshold value, and you have to be within these margins to avoid the undesirable effects. So when we use this knowledge in our chamber, in our setup, we were able to treat the glass in a right design, meaning that we induced volume modification on the glass sample without damaging the surface, and we found out how to ablate very precisely certain region or certain area of the material without causing the cracks or any side damage around the hole. So you can have this very nice structured hole. Use it, for example, for cutting or drilling, whatever. Okay, so thank you. That's all from me regarding the damage threshold. And if you have any questions, I'm now ready to answer it. Thank you.
Thank you, Jan, for your deep dive in to LIDT and your extensive presentation with a lot of real-life examples. I trust our audience has enjoyed the presentation as much as I did, and we'll surely have a lot of interesting questions. Therefore, without any ado, I commence the Q&A session. You're welcome to place your questions using the hand raising button or through our Q&A chat box. So in the meantime, before we receive any questions from our audience, I have one here from Mr. Wilfried during the presentation from Zeiss Micro-Optics, who is asking the following. A common process in micromachining of micro-optics in glass is smoothing with a CO2 laser. What is the typical surface quality of this process?
Okay, this is a bit tricky question because actually the quality is driven uh, by the customer or by the user of the process glass. Because if you want to use this process glass in, for example, lithography, you're gonna need extremely smooth surface. Like the roughness has to be in order of the nanometer. For the optics purposes, the roughness is usually done by lambda divided by 10 at 632 nanometers. So we are talking about the roughness on the level of 60 nanometers or something like that. And scratch dig is usually required less than 20. So over the certain aperture, you should not be able to observe more than 20 scratches or digs. This is for the optics. But if you have some industry glass, then you have to deal with, usually you have to deal with much higher roughness or much lower surface quality. I'm not really sure how good can you be when you smoothen the surface with CO2 laser, because that's a lot of about how good is the person who is doing the smoothing, I would say.
Okay,
But
so
yeah, well, if we to conclude, if we talk about the optical application, we are talking about the roughness, which is tens of nanometers, and about the stretch dick ratio, which is less than 20. Yeah, that's like the straightforward answer.
okay, thank you. I hope we've answered your question by this. Um, so waiting for some more questions to come in. I've got one question to you, Jan. I would like to know how Hilase LIDT can benefit, for example, an optics production company who's developing new optics for new generation lasers, who has an ever-growing power or energy per pulse, with applying our small and big beams during the testing. How can that help such a company?
Yeah, well, actually, the test which you are using for the components should be used in accordance to what purpose you are pursuing with your test. So, if you want to simply compare the properties of two different coatings, for example, you know that the coating you are producing has intrinsically low damage threshold because, for example, choice of the materials, and you want to improve. So you use different materials, you reduce the coating, you reproduce the test, and you compare. Then you see directly whether you get better or not. But if you want to, let's say, certify or prove particular component for particular laser. For example, as we have our Bivoy laser, which currently holds the record of 150 joules at 10 hertz repetition rate, then you have to adapt the test accordingly because there is a big beam with the high energy, and you need to certify the component or the mirror lens window you produce accordingly to the needs of the laser. You need to test it with the big beam to be sure that there is uh, no influence of the thermal stress, for example, because if the beam is bigger, then the absorption effect during the test will be higher, and you will see whether it's happening something there or not. Also, it's much easier with the big beam to find out if we are talking about the large aperture, much easier to find out whether there is any so-called low frequency defect, because as you are increasing the aperture, you have high probability that you will have contamination. And to discover such contamination, you have to scan the whole surface. And if you have small beam, of course, with the small beam, the light surface will take a long time. So the bigger is the beam, the shorter is the time, the better is the chance that you will discover that there is something wrong on the coating, and the more reliable is the result you are providing, and the more sure you can be tell that the respective component is fulfilling the needs of the customer.
So in
So
other words, you can help with selecting the right size of optics for that specific application.
in general, the right optic. We can
Okay.
say we can say that this particular optic is suitable and it can withstand the conditions for the mentioned application. Because yeah, it's the general problem we observe is that when somebody give us 1 inch lens or mirror for testing, we found out that it has certain damage threshold. But when we are provided with the same kind of coating, with exactly the same, prepared with exactly the same process, but on the bigger sample, on 2-inch or 4-inch optics, which is, for example, used in our Vivo, then the damage threshold is suddenly much lower.
Mm-hmm.
So you can't easily transfer the knowledge from the small components to the large component. It's not straightforward.
Okay, so just checking if we've got any questions from our audience. I hope you're not too shy to ask, so otherwise I've got one more question here in on my side. So if someone is, for instance, planning to cool down his optics, can you study the influence of the cooling efficiency with LIDT?
Oh yes, actually I haven't mentioned it in the capabilities, but we integrated to our testing station cryocooling possibility, because there is a lot of high power lasers nowadays coming, which are based on the cryocool media. And we also observe that at cryo temperatures, the damage threshold of the materials in general, and specifically the coatings, are different than during the room temperature. So we are able to measure both the damage threshold at the room temperature, damage threshold at the cryo temperature, with the big beam, with the small beam, at different methods, and compare such results and tell whether the particular material or element is suitable for the cryocooling or not. That's yeah.
Okay, and one last question from my side before I give the floor to our audience if they have got any questions. So you were also mentioning we've got an ISO standard laboratory. So what kind of reports as a customer can I expect that you will provide me? Can you also provide me ISO certified reports?
Yes, as the standard requires. There are certain facts and certain things which has to be mentioned in the test protocol, and if you prepare test protocol accordingly, is ISO compliant. Um, Regarding the conformity declaration, for which the laboratory has to be certified, that's something we can provide as well. Not yet, because or not at the moment, because we are now in the accreditation process. But we are processing ISO certificate, and we are going through the accreditation process. And after that process, we can also accompany the ISO protocol with the declaration of conformity. For example, for space application or aircraft industry, this is something which is quite important.
Mm-hmm. Thank you. Okay, so since I cannot see any raised hands or questions in our chat box, and due to the fact that we are coming close to the time we had allowed for our webinar, if you've got any questions still that you couldn't come up with during the presentation, we would strongly encourage you to mail us your questions to the email address which you will receive with the promised white paper, which will follow soon. We would also very much appreciate your feedback in regards to the webinar, and kindly ask you to participate in our survey, which you will soon receive in your mailboxes as well. So if we don't have any questions from our audience, I would like to take this opportunity to thank you once again for taking your time to join us today on such an interesting topic such as LIDT. And we dearly hope to see you soon in person at future exhibitions, conferences or presentations. So I'd like to wish you all on behalf of Hilase all the best, and stay in touch, be informed. Goodbye.
Thank you too, and goodbye.